Let's now look at a three-phase power problem. This is a Y-connected set of sources, and they are balanced, and it's a positive phase sequence. The A phase leads the B phase, and the B phase leads the C phase. That's the ABC, or positive phase sequence. We have resistance in the transmission line, or R sub L, and in this case I'm setting those all the same, and I'm assuming that that's a purely resistive. There's no reactive element in that transmission line between any of the loads. And Z sub A, Z sub B, and Z sub C, we are going to assume that those are equal and have a value, each of those, of 10 for the real impedance plus J4. That's our system, and the loads are also a Y-connected set of loads, and we have a neutral conductor between the source neutral terminal and the load neutral terminal. The problem that we want to address, actually there's three pieces that I want to look at in this particular problem. I want to find the total complex load power. That means total, that means all three phases. I need to find all three phases complex power and add those up, or somehow come up with that total. We're asked to find the line current in phasor form in the B phase, I sub BB, and we want the power factor of the A phase load. The first thing that we can note is that we are dealing with a balanced system, and the reason why we know that it's a balanced system is because our sources are balanced. They have equal magnitudes, and they are 120 degrees apart, each of those sources. They're also expressed in RMS values initially, and so we don't have to worry about converting. And now all of our power formulas are accurate, or can be used consistent with what we've had before for our complex power formulas expressed in RMS units. Each of the loads, if we look at those loads, each of those loads, or the loads of each phase, are the same. Again, that's necessary for it to be balanced. And the impedance of each of the lines between the source and the load, those have to be equal. And the line impedances, which in this case are real, they're R sub L, but it could be Z sub L. As long as the real part and the reactive part are equal, then those would be a balanced set of lines. We have all of those pieces that are satisfying the balanced conditions, and that allows us then, because of this balanced behavior, we now can analyze just one phase, or one loop, or one mesh. We can analyze a single phase subcircuit, and if we need any other information, we can simply realize that the B phase is behind by 120 degrees the A phase, and the C phase is 120 degrees behind the B phase, which effectively is 120 degrees in front of, in sinusoidal steady state, the A phase. So we can analyze a single phase subcircuit and relate that analysis to all the other phases. And a lot of times it's easier because of the way that people have usually specified the sources. The A phase typically has a 0-degree phase angle associated with it, and for that reason I'm going to concentrate or examine the A phase. And that's since this source voltage V sub AN is a phasor, has a magnitude in RMS and an angle of 0 degrees, and that's in volts RMS. And this fact, the fact that our phase angle is 0 degrees, allows the problem to be a little easier to work. Now let's pull out that A phase and re-sketch it as a single phase. Here's A, here's our source, and that's this V sub AN as a phasor. We have our line resistance, R sub L, and that takes us over to our load impedance, C sub A, which brings us back to the neutral at the load side, and that's connected to the neutral on the source side. This current, I sub AA, in the A phase can now be solved from this circuit problem. Obviously, the current in this neutral conductor, you have to add up all three phases to get the true neutral conductor current, but right now we're just isolating on one phase, and we should realize that the neutral conductor current is the sum of all three if you go back to the original circuit. We can now find this line current, I sub AA, by simply using our techniques that we're familiar with, and that's KVL. We can write a KVL equation for this circuit, which says then that using KVL says minus V sub AN, starting at the lower left or the little n node, we have minus V sub AN plus R sub L I sub AA plus Z sub A I sub AA equal to 0. The only unknown in that equation is I sub AA. We have then that I sub AA is equal to V sub AN solving for I sub AA, R sub L plus Z sub A. For our particular problem, we were given that V sub AN was 100 at 0 degrees, R sub L was 2, Z sub A was 10 plus J4. We now have this is 100 at 0 degrees, this is 12 plus J4. It's probably easier to convert the denominator from rectangular form to polar form. Doing that, we end up with the magnitude of that complex number being a little bit bigger than 12, or 12.65, and the angle is the inverse tangent of 4 over 12, or the inverse tangent of 1/3, and that gives us 18.43 degrees. That we need to divide into 100 at 0 degrees, or 12.6 goes into 100 almost 8 times. 7.905 is now our magnitude of the current, and that's in amps. That's now I sub AA. And you can see that we're not solving this in the order with which we were given or requested in our ABC problem statement, but sometimes it's just easier to do different parts before the others. We weren't asked for the A phase line current, we were actually asked for the B phase line current, but that's the same in magnitude is the A phase's magnitude, and the angle is just 120 degrees behind the angle of the A phase, where this is now theta sub A, the angle of the A phase. Or what we were asked for, which was the B phase line current, that's now 7.905 at an angle of minus 120 minus 18.43, or minus 138.43 amps. That's now one of our three solutions that we were asked for. We also were asked for the power factor of the A phase's load, which is going to be the cosine of the angle between the voltage and the current, but the angle of our voltage and our current is just the impedance angle. The impedance angle, theta sub z of A, is just the inverse tangent of 4 over 10. Our impedance of z sub A, or any of the loads, was a real part of 10 and an imaginary part of J4, and we found that this now gives us the inverse tangent of 4 over 10 is 21.8 degrees. The power factor then of the A phase, and for that reason, since these are equal, it's a balanced system, the power factor of the B phase and the C phase are exactly the same. This is now the cosine of that angle of our impedance, which was 21.8 degrees. That's now 0.9285. It was inductive. It had a positive imaginary part to the impedance, and for that reason its power factor is lagging. We now have found two of the three pieces of our solution. Let's now look for the third piece, and the third piece was the complex power of all three, or the total complex load power. We're now in a position to find the load power, complex load power for phase A. That is several different ways of looking at that, but we know that if we knew the load voltage, the voltage dropped across Z sub A, we could multiply that by the current through that load, which in its conjugate. And the current through that load is just the A phase line current. Well, we haven't yet calculated the voltage dropped across that. Let's just do it symbolically. V sub A n would just be the impedance of the A phase times the current through the A phase, which is I sub AA, and that's now times the conjugate of that A phase line current. We know, though, that the product of a complex number times its conjugate is just the magnitude of that complex number squared, and so we end up with the complex power of the A phase is the impedance of that A phase times the magnitude of the line current in that phase squared. In our particular case, Z sub A was 10 plus J4, and I sub AA magnitude was this 7.905, and we're going to square that. Specific numbers lead us to then the square of that almost 8 is almost 64. It's actually 62 and a half, which says that we have a real part, or we have an average power in the A phase of 625 watts. we have a reactive power of 4 times 62.5, which 2 times 62.5 is 125, so twice that is then 250 volt amperes reactive, and that's an inductive load, which makes sense because our impedance was inductive, and our A phase complex power is then 625 plus J 250 volt amperes. If we now need the total complex load power, which is S sub total, that's just 3 times any of these single phase. Since it's balanced, it doesn't matter which phase we look at. We can just say the generic complex load phase, and that was 625 plus J 250, and that's volt amperes. If we multiply that out, we then have for our total load complex power, it's 1,875 watts plus J times 750 volt amperes. And that's the last piece of the 3 parts that were asked to be solved for in that particular problem. Some possible variations on that, or modifications or extras that might be asked for a 3-phase problem, is somebody might ask you to adjust the power factor of any of the loads, and since it's balanced, you would be adding in the same amount of capacitance to each of the phases, and you can just look at one phase at a time. So we could adjust the power factor, or a variation would be adjust the power factor to bring the power factor to 1 or to bring it to 0.95, but we could adjust the power factor by adding equal capacitance to each load phase. Or somebody might ask, what is the source power factor? And there's a couple ways that you could actually look at solving that problem. You could say, okay, if we need the source power factor, not only do we need to worry about the loads, but we also need to worry about the line power, the power that's lost in the line. So for this one way would be to include, we've already found the load complex power. We would have to find the complex power of the lines between the source and the load to find the source power factor. So we must include the complex power of all loads and the lines complex power. In our particular example, the line complex power would be this Z sub L, and again we could just take the magnitude of our line current and square it. For our particular problem, Z sub L was real, it was just 2, and our line current was 7.905, which when squared gave us 62.5, or we now are absorbing 125 watts in each of the phases in the transmission lines. So that for the A phase, its total power complex is the load complex power plus the line's complex power, which we had 625 plus J 250. That was our load power, plus 125 for the line, or the total A phase power that's being delivered from the source is now 750 plus J 250, or if we put that into polar form, it's 790.6 at an angle of 18.43 degrees. And if we needed it, then we could find the power factor of the source is now the cosine of that 18.43 degrees, which is 0.949 lagging. That's one way that we could solve that particular problem of finding the source complex power or power factor. We could also, we know what the source voltage is, that's V sub AN, and we also know the current flowing through that source, that's just the line current, I sub AA. And anytime we have the voltage and current in phasor form or in complex form for a element, in this case the source, we can now just take the product of V sub AN times A sub AA conjugate. V sub AN is this 100 at 0 degrees. I sub AA was 7.905, which we need to conjugate. I sub AA was minus 18.43 degrees, which when we conjugate that is 18.43 degrees with a positive sign, or this is now 790.5 at an angle of 18.43 degrees, and that's exactly what, and that's in volt amperes, that's exactly what we had above. And because of that, we now can calculate the load or the source complex power two different ways at least. Another variation on this problem that somebody could ask is they could say, oh, what about if you add another set of three-phase loads? And now that's not as specific as you need to be in specifying what's happening. Those loads could be Y-connected, or those loads could be delta connected. If the loads are Y-connected, then you could simply treat each of those loads. You now know what the current is flowing to those. You might be able to then figure out, using a current divider, how much current is going through each of the loads, and then treat them separately. Or you could go ahead and combine all of the impedances of all of the loads, load 1 and load 2. Those will be in parallel if they're now a Y connection with another Y connection, and then you could use that to find the power of all of those. If it's delta connected, it's a little different, because now the impedance in a delta connection is actually bigger by a factor of 3 what a Y-connected load is. If you now had to, if you were given delta connected loads from A to B, B to C, and C to A across the lines, then you could, using this relationship, find the equivalent Y-connected load value, which is just 1/3 of the delta connected load that you were given. And now that you have an equivalent load impedance, you could now move back to this way. You now have another Y-connected load to work with. And repeat what we just said above to complete that particular problem.